Hello friends. Now look at the effects of zeta on the time response of second order control system that was subjected to your unit step input. As we know that the time constant t is equals to 1 by zeta omega n. It means the time constant will be affected by this zeta. So look at the look at the transfer function first. The transfer function of second order control system is equals to omega n square divided by s square plus 2 zeta omega ns plus omega n square. Okay, so you can see here that this zeta will affect this second order equation. So let us find out the roots of this equation, and this roots is nothing but it is actually roots of 1 plus gs into hs is equals to 0, where 1 plus gs into hs is equals to 0 is known as characteristic equation of the system. This may be any system. Okay, so in this way, here 1 plus g of s into h of s is equals to 0, and if we look at the term, then this will be s square plus 2 zeta omega ns plus omega n square. Okay, this is a polynomial in S. So we can write this S as S1 comma S2 equals to minus 2 zeta omega n plus minus under root 4 zeta square omega n square minus 4 omega n square by 2. That is, using this one, that is x1 x2 are the two roots, then this is your minus b plus minus b square minus 4ac by 2a if the polynomial is ax square plus bx plus c is equals to 0. So if we solve this equation, then we will get this 2 zeta omega n with minus sign plus minus 2 omega n under root zeta square minus 1 by 2. Taking this minus sign as common, okay, this minus sign, so that we get the final result as S1 comma S2 is equal to minus zeta omega n plus minus j omega n under root 1 minus zeta square, where this S1 and S2 are the roots of s square plus 2 zeta omega ns plus omega n square is equals to 0. Okay, these are the two roots. So look at the roots here. Let's see what will be the value of zeta and what will be type of roots. That is roots and its type. Okay. So if we set first condition, that is for zeta less than 1, roots are minus zeta omega n plus j omega n under root 1 minus zeta square, and the second root is minus zeta omega n minus j omega n under root 1 minus zeta square. It means the roots are complex conjugate Okay. Second case. Case 2 is for zeta is equals to 0. Okay. Let's see what are the roots. For zeta is equals to 0, this equation, or you can say that roots results in purely imaginary, and the roots are plus j omega n and second root is minus j omega n. Okay, that is roots are imaginary. Third, for zeta equal to 1, for zeta is equals to 1, what will happen in this case? Zeta is equals to 1 will result in two repeated roots, real roots. Okay, and these repeated real roots are minus zeta omega n, that is zeta is equals to 1 minus omega n and minus omega n. Okay, that is the real roots. Repeated. Or specifically we can say that these roots are negative real roots. And if we look at the final for zeta greater than 1, for zeta greater than 1, the roots becomes real with different values. Okay, so the roots are that is first root will be minus zeta omega n plus omega n under root zeta square minus 1, and the second root will be minus zeta omega n minus omega n. Okay, that is, you can say that different real roots. Okay, now let's see the individual case. For zeta less than 1, we have already stated that case 1, for zeta less than 1, the CT, that is time response, will be equal to 1 minus e raised to power minus zeta omega nt divided by under root 1 minus zeta square multiply sine of omega dt plus phi. Okay, this was the response, and this response we have already drawn here. This response, that is, you can see here that this response is under damped response. Okay, so this response is actually your under damped. Okay, means damping in the system response will present there. Now this is here under damped. Okay, case 2. Let's see another case. If zeta is equals to 0, as you know that the zeta is equals to 0, if we put zeta is equals to 0 in this case, you know that the roots are imaginary. Okay, purely imaginary. So if we look at this response, if we put zeta is equals to 0, then we will get e raised to power minus 0 omega nt divided by under root 1 minus 0 sine of omega dt, that is omega n under root 1 minus 0 square multiply t plus tangent inverse under root 1 minus 0 square divided by 0. Okay, so we will get the final result as 1 minus sine of omega nt plus tangent inverse infinity, and this will results in 1 minus sine of omega nt plus pi by 2. So we will get the final result as Ct is equals to 1 minus cos of omega nt. Okay, so the response will be this one for zeta is equals to 0. So here you can see that this is a sinusoidal response and it consists of a continuous oscillations, and it looks like this. If this is your input, okay, so suppose this is your unit input and this is your CT. So 1 minus cos omega t looks like this. Okay, and this response is nothing but this is your oscillatory response. And there will be no damping present here. So in this case, the response will be oscillatory and is known as undamped case. Okay, undamped system will remain in undamped case. Okay. There will be no damping present here. So let's look the another condition, that is your system with case 3, that is when zeta is equals to 1. As we know that when zeta is equals to 1, the roots are repeated negative real. Okay, so let's again start with the same response, that is C of t is equals to 1 minus e raised to power minus zeta omega nt divided by under root of 1 minus zeta square multiply sine omega n under root 1 minus zeta square plus tangent inverse and 1 minus zeta square under root divided by zeta. Okay, so let's start with taking the limit, because here zeta tends to 1, so we have to put limit for this complete equation, that as limit zeta tends to 1. Okay, now again we know that this factor is equals to 5, so we can write this CT is equals to limit zeta tends to 1 minus e raised to power minus zeta omega nt divided by under root 1 minus zeta square sine of omega n under root 1 minus zeta square plus 5. Okay, so let's solve this sine function. So this will look like this, that is limit zeta tends to 1 minus e raised to power minus zeta omega nt divided by under root 1 minus zeta square sine of, okay, let's solve this equation, sine a plus b, using sine a plus b, so sine of omega n under root 1 minus zeta square here we left the term t, so there should be t present here. Okay, multiply cos of phi plus cos of omega n under root 1 minus zeta square t multiply sin of phi. Okay, so let's close it. Now substitute cos of phi is equals to zeta and sin of phi is equals to under root 1 minus zeta square in about 1. So we get c of t, that is limit zeta tends to 1 is equals to limit zeta tends to 1 minus e raised to power minus zeta omega nt divided by under root 1 minus zeta square multiply sine of omega n under root 1 minus zeta square t. Okay, and here we get zeta, so cos of omega n under root 1 minus zeta square into t into under root of 1 minus zeta square. Okay, so if we substitute the individual limit in this function, then this results in, that is omega n under root of 1 minus zeta square into t. Okay, and if we substitute the limit individually in this function, that is cos only, then this will result in, because cos of 0 is equals to 1. Okay, so the function will be converted into limit zeta tends to 1 minus e raised to power minus zeta omega nt divided by under root 1 minus zeta square. Here we have to write omega n under root 1 minus zeta square into t into zeta plus under root of 1 minus zeta square. Okay, so if we solve this equation, then we get finally that this will be equal to c of t is equal to 1 minus e raised to power omega nt multiply 1 plus omega nt. Okay, and you can say that here this response is actually exponentially rising response, because here in this case this factor, that is this factor, is decreasing with time, so the complete equation will be increasing with time. So in this way the response looks like this. Okay, suppose the input is this one, this is your unit step input. Okay, and here this is your time and this is your ct. Then ct, because it is your exponentially rising function, total is your exponentially rising function, so it's looks like this. And this is here 0.02 unit and this is your 0.98 units. from this to this. Okay, so this is nothing but this is your C of t, and you can see here that there will be no oscillations present. Okay, but however, if we switch our limit from zeta is equals to 1, let us suppose this is your zeta is equals to 1. Okay, here this side, this is your zeta less than 1. Here this side, zeta greater than 1. And we know that just before this region, that is in this particular region, the system will be your underdamped case. It means this is the case with critically damped case. Critically damped case is that case where the oscillations just stopped. The condition where the oscillations just stopped. Okay. This is your critically damped case. Now, finally, if we find out the response for case 4, that is for zeta greater than 1. Okay, as zeta less than 1 will have some oscillations, but it are underdamped. Here you can say that your damped oscillations are were present there, like this here in this case. That is in this particular case, that is damped oscillations were there. But when we substitute zeta is equals to 1, then no damping will be there. Now what will happen if we increase zeta beyond 1? Then the response should looks like this. That is like this. That is, this will be your for zeta greater than 1, and this case is nothing but this case is for over damped case. Okay, so if we look at the response, I am directly calculating its response here. Then the CT will be given by 1 minus e raised to power minus zeta minus under root zeta square minus 1 omega nt divided by 2 under root of zeta square minus 1 multiply zeta minus under root zeta square minus 1 plus e raised to power minus zeta plus under root zeta square minus 1 omega nt divided by 2 under root of zeta square minus 1 multiply zeta plus under root of zeta square minus 1. Okay, so this will be the response for, you can say that, over damped case. So the response will be over damped. Okay, and if we separately draw its response, then it looks like this. Suppose this is your T here, and this is your CT here, and this is your input function, then the response will be like this. This is for overdamped case. Okay, this is your overdamped case. Now, if we look at the locations of these roots, then for a given value of omega n, the roots of characteristic equation will lie at either at imaginary axis or at in the negative real part. So it looks like this. Suppose this is your plus real and this is your minus real, because we have to draw the roots of this polynomial, that is 2 s square plus 2 zeta omega ns plus omega n square is equals to 0. Then assume that this is your real axis and this is your plus imaginary axis and this is your minus imaginary axis. Okay, so again go back to the this distribution, that is for zeta is equals to 0, the roots are at imaginary line and these are purely imaginary. You can say that these are your purely imaginary. So suppose that for a given value of omega n we want to draw, so the roots, let us suppose, lie at this position and this position. This is nothing but this is your plus j omega n and this is your minus j omega n. And if roots are complex conjugate, then it will lie in this particular region, that is in this particular region. Okay, so let us suppose the roots are like this. And if the zeta is equals to 0, zeta is equals to 1, then the roots will be repeated. So you can say that the roots will like this, and here if zeta is greater than 1, then one root move this way and one root will move this way. Okay, so this is the case if roots are lying at this position, then zeta is equals to 0 and the response will be oscillatory. Okay, if the roots are at this position, that is for zeta less than 1, then the response will be damped response. Okay, if the roots are lying at this position, that is zeta is equals to 1, then response will be your, just you can say that critically damped. and if the roots are lying at this position, that is for zeta greater than 1, that is for this one and this one, then it looks like this. Suppose this one is this, then response will be looks like this. Okay, this is your CT here, this is your CT here. Now, if we find out another relation, suppose that this is your phi. Okay, this phi is nothing but this phi is your cos, sorry, this is your phi, this phi is your, let us suppose this is your theta, not phi. This cos of theta is zeta. This implies that theta is equals to cos inverse theta. Okay, and this distance will be equal to omega n under root 1 minus zeta square, whereas this distance will be equal to zeta omega n. Okay, thanks for watching this video.